So when it comes to the shear design, we started last time, we looked at the testing, type of cracks and type of failure, mode of failure when it comes to flexure versus shear failure, direction of failure, section of critical shear, or this gave you the critical section of shear if you like to call it this way. And as I said that you are going to take it at the distance away from face of support. So if this is here the support, this gives you the face of support, and you're going to be going here the distance from the face of the column. It is very common that when someone gives you here the span of the beam is going to be measured from the center of the column to the next center of the column. And we call this center to center span. But when you take, let's say, measure from the face of support, like in here, to the next face of support, we call this clear span. So we need to differentiate here between clear span and this one here, we're going to be calling it, if I like to start from here, let's say center of column to the next center of column. I'm going to be calling this just the span, if I just say the span, or I may call it also center line to center line span. In bridges, in many cases, the support is not like a column. The support is going to be this bearing. And in this case, face of support is going to be right here. So you need to go here, D distance. Now, what is D in this case? D in this case is going to be the distance from the top compression of the beam to the tension rebars. So I'm assuming here the tension rebars is going to be right here. It's going to be running like this. And this one here is going to be D distance. I may point at it here and just call it here D distance. Let's give you the depth. We said also if the structural support is going to be like a hanger, we don't have here a chance for failure to be taken 45 degrees. Definitely is going to be happen like this. Critical section of shear is going to be right at face of support. While in this case, the failure is going to happen like this. And this section is going to act as a column cap. This piece here. It's going to stay with the column, failure to happen. Here's going to be the same. It's going to happen like this. But here, it will just happen vertically. Same thing here, if you put big concentrated load within the D distance, failure is going to happen right at face of support.
Professor, is that why we use, I think, filleted areas or filleted corners? Filleted.
Use what?
Some people say fillet, some people say fillet, where it's kind of like an arch or a rounded corner.
No, this is different. It's a little bit different.
Because that would be considered, because we're using the 45-degree angle because that would be a chamfered, like the shear happens in the chamfer of section C, right?
What do you call here the chamfer? The chamfer is when you have a corner like this, right? And then you'd like to break it. So you do something like this. This is the chamfer.
Right, right.
So this is what you call here a chamfer. Here is not really a chamfer.
Oh, okay. I see what you mean.
It is when the failure is going to happen, failure is going to happen at 45 degrees. And this piece, you put this piece here. This piece of the beam, let's say the beam before failures look like this, right?
Right.
During failure, it's going to be happening like this. It's going to be coming down this way. So this piece here is going to stay with the column. This little piece is going to stay with the column. It is true, it's part of the beam, but it's going to be staying with the column. So we call this is like part of the column. We call this the column cap. And the beam is going to be fading down like this.
Okay, thank you.
Yeah. If you like to figure out here the load demand, you need to continue with the load combinations that we used before. Just repeat them. When it comes to strength, strength is going to be based on the concrete and the steel. Concrete strength is going to be called with this equation. This is the concrete without the phi factor. Phi factor is going to be 0.75 for the concrete and steel when it comes to shear. We don't have a graph for it. We don't have anything similar to the flexure phi factor. It's going to get changed based on the amount of strain in the steel. Instead, we're going to have just one value here, 0.75. Concrete strength is going to be equal to 2 square root of F prime C times the sheared area. So this one here we call the shear factor, if you like. Square root of F prime C is going to be the strength of the concrete at 28 days. And it has here a maximum value of 100 psi for the entire value, which means maximum F prime C would be equal to, you can see here, F prime C in this case is going to be equal to 10,000 psi in this equation. So that square root of that is going to be equal to 100 psi. BW and D is going to be the width and the depth of the beam. So if you have a T section, you just take the web width. You don't take the entire T section, just the width of the web itself. Now for the steel is going to be the ties. And VS, which means the shear strength provided by the steel, is going to be equal to the following. Now let's take it here as pieces. So I'm going to say VS is going to be the shear strength of the steel. And again, you need to multiply it eventually by the phi factor of the 0.75. D is the depth that we use for tensor reinforcing. So this is going to be the same depth. Fy is going to be the yield strength. It says here sub T because it's going to be for the ties. In the past, they used to have ties made out of grade 40 steel. Not anymore. Now the common is going to be also 60, very similar to the longitudinal reinforcement. So now understand this, understand that. Now what is A sub V and what is S? This is going to be two variables that they go together. We went through this already, but also I'd like to back check it for quick with you guys. If you see here, if you cut a section like this, and for each tie, how many sections are you cutting? I'm going to say I'm cutting it through one and through the second. So in this case, A sub V is going to be the total cross-section area of one tie set. So let's say if you ended up with maybe 3 vertical legs, in this case, you're going to be taking 3 times the cross-section area for just one rebar. So AV is going to be for one set of ties. You just do the total cross-section area of them. If you have number 4, I'm going to assume here, say number 4, rebar for the ties. A sub B equals, which means 1 rebar number 4 is going to be having 0.2 square inches. In this picture here, I'm showing 3 rebars that I'm cutting through. So A sub V is going to be the shear area is going to be 3 times 0.2. It's going to be equal to 0.6 square inches. And this is what you would use in this equation. This is going to be A sub V. This is going to be the cross-section area of the ties resisting shear. S is going to be the spacing. I'm going to go back here to the same detail. As you see here, S is going to be the spacing between 2 sets of ties. Why do I call it set of ties? Because I may just end up by putting 1 rebar in the middle, or maybe a couple of rebars in the middle, like cross ties. And in this case, I may have 3 or 4 rebars. And they're going to be happening in the same location, right next to each other. So in this case, I'm going to call this a set. Let's give another set, third set, and so forth. So S is going to be the spacing between the set of ties. Okay, the equation looks simple. Also, when you look at the maximum value, it says now it is related to concrete. It's going to be 8 square root of V prime C. I'd like to compare this equation with the previous equation, the one that I used for concrete. For concrete, it says it's going to be 2 square root of V prime C. Here it says 8 as the maximum for the steel. So total for steel and concrete, if you like to add them together, it's going to be 8 plus 2. You're going to have a total maximum of shear stress is going to be 10 square root of V prime C. Which means The lowest shear strength for a concrete section with no reinforcement is going to be 2 square root of F prime C. Of course, times B times D, which means times the sheared area. When you add the steel, you can add amount of steel for shear resistance, and the shear strength is going to be ranging from 0 square root of F prime C, if you are adding very little amount, all the way to 8 square root of F prime C. So you can control here the amount of steel that you add there to control the amount of total resistance. Of course, this is going to be based on the demand that you're asking the beam to support in terms of shear. Also, the code says here, if the demand is going to be very low when you compare it with the strength, what does it mean by this? Let's say I did this equation here, and phi VC, I'm going to call it here F phi VC I'm just assuming here, I'm going to say V sub U equals, in one of the beams, I was doing some analysis, it's going to be equal to 50 kips. So fine. I did V phi C. It's going to be V times VC. Only strength for the concrete, including the phi factor. It turned to be equals to 60 kips. So now the strength is going to be 6 kips for the concrete only, and the demand that you want the beam to support is going to be 50 kips. Now apparently you're going to say I have enough strength by the concrete to support the shear demand. Now do I still need to add some ties? And the answer, yes, you need to add some ties. It's going to be minimum amount of ties that you need to add there. It is true that the concrete strength is enough, but you still need to add some minimum ties. Where'd you get the equation from? I'm going to say minimum ties is going to be based on these two equations. So great. Now it's going to be very clear to me. If I have situation like this, I need minimum ties. So it says here, provide minimum AV, which means ties. Fine. Have another example. I have V sub U is going to be 50 kips. The shear strength of the concrete only is 120 kips. Just different beam, right? You're going to say now the concrete beam is so strong compared to the demand that you have in there in shear. Do I need to provide any ties? We go here to the next slide. According to this condition here, it says no ties are needed. You don't really need any ties. If V sub U is going to be smaller than 1/2 of the concrete strength. Now let me go back one slide. The strength in this case is 120 for the concrete, and the demand is 50. So this demand is lower than 60, is lower than 1/2 of this capacity. In this case, no ties are needed. So I'm going to say here, no ties are needed. Any questions? So good about this? Ties are not needed when the demand is going to be very small. What does it mean by very small? When it is going to be lower than 1/2 of the concrete strength in shear. So, okay, this is very good. I guess it's clear to me. Now the ties, in order for you to provide some ties to resist the shear, you need to hook it with the top reinforcing. So you need to have some reinforcing here. And of course, you're going to have reinforcing at the bottom. So I'm going to say at least you need to have 4 rebars, 1 at each corner, to think or to consider this tie to be resisting shear. Say fine. Or you can have the tie this way. It can be built up of 2 ties. This give you like cross tie. And also what's important is that you provide some reinforcing here, top and bottom. So it's going to be the same reinforcement that I have here. I can just copy it here if you like. Now, in this case here, when you cut a horizontal section, you're cutting through 2 rebars. And A sub V is going to be equal to 2 times the cross-section area of the tie. Same thing here. If you cut horizontal section, not a vertical section, a horizontal section, you're cutting through 2 legs of the tie. So the same cross-section area here is going to be 2 times cross-section area for 1 tie. Now, how about here? What I'm doing here, I'm providing 2 of this tie and just put them next to each other. So it's going to be one set. We're going to call this one set of ties. It's going to be right next to each other. It's going to be touching each other. We're going to keep repeating this on an S distance spacing. Now let me check this out. With this section here, I'm cutting through 1, 2, and 3, and 4 rebars. So A sub B here is going to be equal to 4 times A sub B. So let me put it here. So A sub B in this case is going to be equal to 4 times A sub B. How about here? I'm going to say here is going to be only 2. So I'm going to say A sub V equals 2 times AB. Why? Because I have only 2 ties that I'm cutting through. This one, of course, is going to be same like here. This one, of course, is going to be same as here. Okay. We have this example, which exactly this first example that we went through when it comes to flexural design of beams. And it says here, determine the shear strength adequacy for the beam section shown below. Here's the beam section. The width 10 inches, total depth is 16 inches. And the depth to the tension rebars is how much? Now let me figure this out. Let's say the tension is going to be up to here, which means the depth is going to be from here to there. It's going to be this depth here, right? It's going to be the depth D. This depth D is going to be equal to 16 inch. You subtract what? The clear cover. And the clear cover is going to be measured to the bottom of the tie. Look at this. Subtracting the tie diameter. And this is going to be number 4 pi. Therefore, this is going to be like half an inch for the tie itself. Also, I have the rebar diameter. As you see here, is going to be number 8. Meaning, from here to there is going to be an inch. Therefore, from here, from this point to here is going to be half an inch. So I'm going to say this distance here is going to be half an inch. Right? Which means it's the distance. And the tie diameter is going to be half an inch. So with that, I have 1 inch from this red line to that red line. Plus 1.5, it means 2.5 inches from the center of the rebar to the bottom of the beam. So take 16 minus 2.5 is going to be 13.5 inches for the depth.
Professor, you said number 4 tie, the diameter is 1/4
inch.
Mm-hmm.
Number 4 is going to be half inch. Where is
Okay.
this? It's going to be this guy from here to there. So this
Got
is
it.
half inch. This guy here is half inch. I have a total of 1 inch from here to there. All right, it says here that the beam center line to center line span is 22 feet. I guess if they didn't say center to center span, I'll understand that this is going to be center to center span. As I said there, that either that we're just going to be calling the span or center to center span. This is what I'm talking about. Center to center span or just the span is going to be the same thing. Unless he didn't say clear span, it means center to center span. So it's going to be 22 feet. And the clear span is 20 feet. So how big is the column? It's going to be the question. I need to figure this out. I need to draw it and figure this out. Dead load is given as 1.5 kip per linear foot. And live load is going to be 0.7 kip per linear foot. Question to you. If I give you the dead load this way, 1.5 kip per linear foot, does this include the weight of the beam itself? I'd like to hear from you guys. Alfred? Yeah, Alfred, are you there? Alfred?
Yes.
Yes. If I give you here the dead load to be 1.5 kip per linear foot, does this include the weight of the beam itself?
Yes.
So it is included. So do I need to add it? Do I need to add it to this, or this is enough? Do I need to do calculation of the self weight of the beam, or this is enough?
I think that's enough. Is it already included?
Yes. All right. Thank you. The concrete strength here was given as 4,000 psi, and of course I need it because of the shear strength. The steel yield strength is going to be 60 psi, and of course this is going to be for the ties and this longitudinal rebars. It says here determine the shear strength adequacy. What does it mean by that? It means find out the demand, find out the shear strength of the ties and the concrete, and compare them to each other. Load demand here is given to us as 1.5 kip per linear foot. For dead load and live load, it's going to be 0.7 kip per linear foot.
Professor, just for clarity, so the dead load includes the distributed load includes
Yes.
the, okay.
Yeah.
Thank you.
Give me a second, please. Give me a second. So dead load and live load given to us. 1.5 kip per linear foot, and live load is 0.7 kip per linear foot. I'm going to be using here the load combinations. Load combination means you're going to try here 1.4 dead load versus 1.2 dead plus 1.6 live load. We tried this number that you guys now are good with, and turned out that this load here is going to be controlling my design. This is going to be the 2.92 kip per linear foot. Very similar to the first exercise that we have done for rectangular section with tension reinforcing only. So it's going to be 2.92 kip per foot. This is great. Now I have that. Now I need to figure out the shear demand. Now this reminds me here, if I'm going to go back a few slides, critical section is going to happen at 45 degrees, which means at the distance away from face of support. So I need to draw it and see where exactly the shear is going to be happening. Draw this. Say, okay, here's my beam with two columns. Center of support is going to be right here. This is how we draw it. So the structure system is going to be like this. This is going to be the one that we are used to. And also this is going to be the center of the support. Center to center distance or span is going to be 22 feet. That was given to us. I didn't make this up, that was given to us. The clear distance is 20 feet. Therefore, I'm going to have here a foot from each side, so that the total is going to be 22 feet from center of support to center of support. Now let me draw the column. My column is going to be like this. It's not going to be just like this. It needs also to go out to this location. So most likely, this column width is going to be equal to 2 feet to the right, and the same thing here to the left. Okay, I guess, so I'm clear on this figure that I'm just drawing here. The depth, I guess we calculated this before, and it says going to be 13.5 inches, and you guys know where it's come from. Now I should be able to draw the shear diagram. Usually when you draw the shear diagram, you draw it from the center line to the center line. This is the way we're used to. So to figure out the reaction in each side of this beam, This reaction is going to be equal to the total load, 2.92, times the span, the 22 feet, center to center, divided by 2. I'm going to do it here. Well, it's not there, but let me do it here. So I'm going to say for the reaction, going to be 2.92 times 22 divided by 2 equals, is going to be 32.12 kips, which is right above. So good. But I cannot use this as my shear demand. My shear demand is going to be at d distance away from face of support, which means it's going to be right here. If you take d distance, it's going to be at this location. Now, how much is the distance from here to there? See, the distance gave you first this foot plus the depth, 13.5 inch. So if you like this distance, I'm going to say this distance equals, I'm going to say it's going to be equal to 12 inches, which is a foot, plus 13.5. Now you'd like to have it in feet. So you'd better add them to each other and divide here by 12. How much is this? Can someone help me? Alfred, can you help me please with this?
Yes.
Yes. How much is that?
2.125
foot, right? This is not an inch. And this distance, my understanding, this distance is going to be for this length that I'm just drawing here, from here to there, correct? Do you agree, or did I do a mistake here, the way I'm marking it? Yes? Maybe this distance, yes? Or you don't really agree?
Is that from the center to the effective depth?
The center to the critical section. So what do you call this? We're going to call this critical section of shear.
And that's the 13.5 inches?
Critical section of shear. It's going to be a d distance away from face of support. Here's the support. Let me put this aside. This is going to be the face of the support, right? You go d distance away from it. So from here to there is going to be 13.5. So total distance from the center of the beam or center of support, center of column, to the critical section of shear is going to be equal to 2 feet, 2.125 feet. Any comments on this? Any questions?
Where does the 12 come from?
From here, the foot.
Oh, okay, it's the foot. Okay.
This is the foot.
Okay, got it.
You can write the equation differently. You could have written it as 1 plus 13.5 divided by 12. This also works, if you like. Same distance, I'm going to have it from this side. What do you mean? If you like here to look for the critical section of shear from that side, this distance from here to there is going to be equal to how much? Exactly same distance, right? Because of symmetry. This is going to be the same as here. It's going to be also 2.125 feet from here to there. Now let's draw the shear diagram. When you draw the shear diagram, in one side you're going to have the reaction. You go up 31.12 kips, and then down from this side you connect them with a straight line. This point is going to happen right in the middle of the span. It's going to be point of zero shear, point of maximum moment. We know about this. The slope of this line is equal to this W, to the weight. So I'm going to say the slope of this line, I'm going to put it there. The slope equals W ultimate equals how much? 2.92 kip per foot. Meaning, if you start here at 32.12, for each foot that you move this direction, the shear diagram is going to be dropping down by 2.92 kip for each foot that you walk in this direction. So good. Let me confirm this. They said that this is going to be the 0 point. And I'm telling you here that for each foot that you walk in this direction, the amount of shear, which means this height, is going to be dropping by 2.92 kip per foot. Let me confirm the shear at this point. And is it true it's going to be equal to 0 or not? So let me write an equation for it. Equation for the shear is going to be saying V equals 31.12, subtracting the distance, I'm going to call it here X, times what? X times what? Times 2.92. So you can call it 2.92 times X. Do you guys agree with this equation? Now someone's going to say, where's X? I'm going to say, well, are you interested in the shear at any location? What do you mean by any location? Any location like here, the shear here. I'm going to say, give me the shear at this point. The shear height here. How much is this ordinate? So someone's going to say, if you want to find out the shear at this location, it is simple. Shear at this location equals the reaction, 3.12, subtracting uniform load multiplied by X. Now where is X? I'm going to say X is going to be this distance that I put an arrow on. This is going to be X distance.
Professor, how'd you get the resultant U again?
The resultant is going to be total load divided by 2. 3.92 is right here. 290 uniform load multiplied by 22 divided by 2, because you have 2 supports and you have symmetry, they're going to be exactly equal to each other.
Thank you.
No problem. All right. So my equation here is going to say the shear at any section, at any point, this shear, which means the distance from here to there, the ordinate for the shear diagram, is going to be equal to the reaction, the 31.12, this reaction, subtracting uniform load times X. What is X? The distance that you walk away from this support coming this way. Means.
Professor, shouldn't that be 32, not 31 for the V?
Thank you. Yeah, 32. Thank you. You're awake, Adolfo. Thank you. All right. So this is going to be equal to the reaction subtracting this uniform load times X, which means for each foot that you're going to be moving that way, the shear amount, which means the shear diagram, the ordinate, is going to be dropping down by 2.92 times the distance that you walked it, that you moved from the support away from support. I said, okay, great. Now I understand this equation. Now I need your help. When X equals, let me take it here to the center of the beam. How much is this from here to the center? I'm going to say this is here 22. It means X is going to be equal to 11 feet. I'm going to say when X equals 11 feet, how much is the shear? Can someone help me with that?
0.
Okay. Someone else? Are you sure? Ramin, are you sure?
Yes. Yeah.
Alexander?
Yeah, I got 0
Can you help
as well.
with this, Alexander? Alex? Are you there?
Yeah, what happened? I don't get what's going on, that's why.
Okay, so stay with me, Alex. I'm gonna have another question here for you.
Okay.
Are you following with this equation or no? Not really.
No.
Okay, a good thing that we are recording this video. So please, I want you to look at what we're talking about here. And just, you know, I was trying to develop an equation for the shear diagram so that at any point you should be able to find out the amount of shear here, right? Because I'm not going to be taking this reaction as my ultimate shear. And instead, I'm going to be taking it at the distance from face of support. All right, Alex?
Yeah.
Okay. So my question is, because I'm not confirming this yet, I was able to come up with this equation. Equation says the shear at any location, like any ordinate for the shear diagram, this height,
Mm-hmm.
is going to be equal to the reaction
Got it.
subtracting the uniform load times the distance that you walk away from this support. Because the slope of this line here equals 292 kip per foot. It's like as if you spend some money, right? So they're telling you here, 1 foot is going to cost you $2.92, let's say, just to make it simple. So you start here with this amount of money inside your pocket, and for each foot that you walk away from this support, you will lose $2.92 per foot. Would that make sense, Alex?
Yeah, it does. Thank you.
Okay. So I put here this equation, say the shear equals the reaction subtracting the uniform load 292 times x, the distance away from there, from the center of the support. So I decide here to double check that this point here is going to have a zero shear. So I said, how much is the distance from this, the middle of the beam, to the center of support? Can you help me with this, Alex?
Wouldn't it be 0?
What's going to be zero? The distance from here to there is going to be 0?
Yeah, because you said it'll be in the center, right?
Yeah, how much is the center? The distance from the center to the support. How much is that?
11.
11 feet. And how much is the shear in this case? Can you try this equation? I know it's going to be equal to 0, but I want to confirm it, and I feel that there's a mistake in the numbers. So I want you please to double check it with me.
Yeah, it'll be 0.
Okay, thank you. So stay with me, please. I'd like you to try when x equals. I'm going to be taken here to this face of support. Face of support happens at this distance here. When x equals 2.125 foot, how much is the shear in this case? I need your help with this, Alex.
$25.91.
9.1? Okay,
Yeah.
I'm going to go with that. Here's the analysis I have done, and I'm showing it's going to be equal to 25.92, which is very close. Just depends if you're doing it with an Excel sheet versus a calculator. And as you see here, this is going to be the shear demand that I'm talking about. This is going to be the ordinate, which means this height from this point to that point. And this is the shear that I need to design for. This is going to be V sub U, right? So now I guess I have an understanding where I get this from. Thank you, Alex. Thank you very much. All right, good job. Now, let me take here a look at the strength. Yes, Christina, you have a question?
Yeah, I was gonna ask why are we interested for finding the shear at that distance? So I know it's VU. Why is it relevant in this case?
Yeah, excellent question. Can I take you back a couple of slides? We wanted to figure out the shear at the critical section. So we call it here critical section of shear. You understand that usually the reaction is going to be higher than, it's going to be like the high shear. I may take you also forward to our shear diagram. Where is the high shear? You say high shear is going to happen at the center of support. Do you agree? Look
Yes, at the two ends.
Yeah, exactly. This is going to be the highest. Now the code says you don't really need to take this and call it your shear demand V sub U. You can reduce it a little bit. To where? You just take a critical section of shear to be at D distance away from face of support. And they say, okay, thank you. But why would you reduce it for me, right? Because someone would think and say, the critical value is going to be equal to 32.12. But you let me use here 25.9. You reduce it for me. This is nice, right? Nice of the code. But you'd like to know the reason of this. Why would you do that? They say because if shear failure is going to happen, it is not going to happen right at the center of the span or the center of the support. If shear is going to happen, it's going to happen in reality at the distance away from support. So just imagine this gave you the beam before it fails, right? You start to put some loads from the top like this. You start to push it down. This piece is going to be coming down with the force. It's going to be coming down like this. So the section of shear failure is not going to be in the center line. It's going to be at the distance away from face of support. So the code recognizes this issue, and they're telling you, don't take the maximum reaction and consider to be your shear demand. Instead, reduce it a little bit because the actual section of failure is going to happen at the distance away from face of support. Does it make sense, Christina, or not really? Yes? No?
Yes.
Okay. Should I repeat it or discuss it further? We're good?
Actually, can you repeat it?
All right, no problem.
Thank you.
Anyone else want me to repeat it?
Yes, please.
Okay. All right. So when you look at any simply supported beam and you look at the maximum shear, it happened at both ends of the beam, which is going to be the reaction. Like, where's the reaction here? Is going to be this number and this number. So someone's going to say simply, let's just take this value here and consider it to be the critical shear. So this here is going to be equal to V sub U. Right? Let's just take it this value here. But whoever has written the code, he's trying to be more realistic and he'd like to be nice to us. They say, no, don't take V sub U to be right here, to be this big value. You know that the shear diagram is dropping down when you go further away from the support. They say, you know what? Take it at the distance away from face of support. Take it this value here. Don't take this. This is going to be just too much for you. I said, okay, this is nice of you that you are reducing here the shear demand for me from the 32 to the 25. But what is the reason behind it? Why are you guys reducing the shear demand for us and make it at the face of support and not at the center? They said, we looked at shear failure of many beams. We did testing, we looked at all failures, and we find out that the shear failure doesn't happen at, if you look here, it doesn't happen at face of support. I said, okay, so what does it mean? Are you saying that the shear is not going to happen here? The column is not going to split into two pieces? They said no. Then I said, don't you think it's going to happen at face of support? They said no. They said, you know what? Look at the failure in the testing. Here's one failure situation. Now where is the shear failure? Where is the critical section for shear? I said, well, it happens right here. It's about here, right? Actually, this is very shallow. It's not really 45 degrees, it's gonna be less. But let's say it's gonna happen about here, right? For this big crack. So this distance from here to there, to the top of the slab is the distance, which is gonna be exactly the same as from here to there. And look at the slope of this line, almost 45 degrees, nearly. How about this shear failure? Look what happened. They said, well, here is the face of support. Look at the failure. Did it happen right at the face of support? They said no, it happened like here. So let's say it's gonna be happening maybe about here, the distance away from face of support. Let's look at other shear failures. Has the failure happened here? I said no. You see this piece here? It acts as a part of the support. So if you take here the distance away from face of support, I'm going to be taking it from here. We take this out. Let's take this at 45 degrees, roughly this 45 degrees, right? This is going to be here the critical section of shear. This is where the failure happens. I'm going to go back here also. Well, that was the shear failure example that we have. So it makes sense that you don't really need to take the shear failure or the shear demand to be at face of support, and also you don't really need to take it as a reaction. It's going to be much less in this case. I said, okay. Also this case, look at this. Go here 45 degrees away from here. They say, take the critical section of shear to be right here. I said, great, thank you. And this is nice that the code here recognizes that shear failure will not happen at face of support or not at the center of support. It's going to happen at the distance away from face of support. Therefore, the amount of shear that you need to design for is going to be slightly lower than what you have here at the center of support. Okay. Let's look here how it happened. I was able to develop an equation for the shear gradient. And this equation, it says, if you have the reaction here, for each foot that you're going to be walking away from the support, we're going to be dropping in it for 2.92, which means this uniform load times x the distance that you're going to be walking. With that, we were able to figure out that the shear demand at the critical section of shear, which means right here, is going to be 25.92 kips. So you don't really need to design for shear demand of 32, which is a reaction. You can reduce it a little bit because of that reason with the code. So, okay, good. How about the strength of the concrete beam? So, well, we have our equation. Our equation says phi times 2 square root of v prime c. I'm going to go back here quick just to show you the equation. Here's the equation. 2 square root of v prime c times bw times depth. Okay. Here's the phi factor, the 0.75. 2 square root of f prime c. Here's the square root of f prime c, the 4,000. Here's the 2, shear factor. Now, where's the width of the beam? I'm going to say width of the beam is going to be 10 inches. The depth, 13.5. You divide here by 1,000 to put it in kips. Easy equation. Now I have the shear demand, shear capacity for the concrete. Now, how much is the demand again? Demand was equal to 25.92. Still higher than what the concrete can resist. So I really need to have some reinforcing, like ties. The tie is provided to me, so I'm not going to be coming up with the tie configuration. Instead, they tell me here that the tie is going to be number 4 ties at 14 inch on center. The tie is predetermined for me. I'm just here checking the adequacy for the beam to resist shear. So I'm going to move forward here to the steel resistance in shear. So, okay, it's going to be equal to A sub V. What is A sub V? Is going to be the cross-section area of the ties in a horizontal cross-section. If I take a section here, it's going to be 2 rebars that I'm going to be cutting through. Let me go through this again and say, let me cut this section here. I'm going to be cutting through 2 number 4. Now move forward to the equation. 2 number 4. Number 4 has a cross-section area of 0.2 square inches. It's going to be 2 times 0.2. The steel is grade 60, so FYT is going to be equal to 60. Depth, 13.5, and the spacing is 14 inches as given. I have shear strength nominal of 23.14. So, okay, let me find out here, this is going to be nominal, and this is going to be what? This is going to be the capacity. Let me find out total phi Vn. It's going to be equal to phi Vc plus phi Vs. It's going to be equal to 30 kips. How much is the demand again? I'm going to go back here one step. The demand is 25. Now think about what happened. If you decide to take the reaction here and use it to be V sub U, it means your beam is not good in shear, because your capacity is equal to 30 kips and your demand is going to be 32. So this is not good. We're just lucky here that the code is reducing the shear demand to be at the distance away from face of support. It's going to be the 25.9. Now your beam is going to be okay in shear. But if you did not follow the code and use the shear demand at center or at the support reaction, this is not going to be good. Your beam is going to be bad in shear. Any questions? No questions?
Actually, yes, Professor.
Yes.
If we do end up using the 32.12, would there be any way to actually make it work, like through adding more reinforcement?
Yeah, very good idea. So I need your help with this. Can you help me with this again? Okay. I'm gonna say here V sub U is equal to how much? 32.12 kips. All right, so stay with me. Are you there?
Yes.
Okay, Alan, let me put your name. All right, how can I figure out the reinforcement needed? Well, you say at least concrete strength and the steel strength is gonna be equal to the demand. Don't you agree? Which means phi, this is gonna be the phi factor times VC plus VS is gonna be equal to what? How much? What is the minimum?
It would be 0.75.
No, it's gonna be equal to what? Like numerical value.
Would it be the 32.3?
Yeah, very good. Good done. Stay with me. How much is VVC? Just
The
VVC.
the VDS, V underscore C, right? The
VVC. You see it there?
yeah, the 12.8.
Okay, so I'm gonna say here, if you like, I can say phi VC plus phi VS equals again 32.12, correct? Phi VC is 12.8 equals 0.75 times VS is gonna equal to the demand. Am I correct?
Yes.
Tell me here
And
the VS value needed. This is gonna be VS needed, isn't it?
yes.
This is not the VS provided. This is gonna be the needed value, right? Otherwise, the beam is not gonna be good. How much is that?
Would it be 25.76?
Yeah. Thank you. Kips. This is very good, right? Now I have an equation for it. You see this equation? Right?
Yes.
This equation says it's gonna be 23. So you'd like to increase it and make it 25.76. What do you want to change here? What is the easiest thing that you can change in this equation? Do you want to change the yield strength of the steel?
Yes, because you would just use a different type of steel, correct?
So is this something okay with you? Would you change the steel only for this beam, only for the ties, for that reason? What is the easiest thing that you can do in the beam? Do you want to change the width, the depth? Do you want to change the depth of it?
The spacing.
Isn't it spacing?
The spacing. Thank you. Who said the spacing? That was right.
It was me and someone else, yeah.
Okay, Oscar and Raman, right?
And me.
And Daniel. Thank you. So you'd like here to change the spacing, right, Adam? I want you to here to stay with me.
Yes.
It was mainly you. So what do you want to change the spacing? Do you want to increase it or reduce it? I want to hear it from you now.
Reduce it.
Reduce it. So what number do you want to try? I'm gonna put it right
10.
there.
10.
10 inches. I make okay. Use S equals 10 inches. Now, can you make it now? Can you give me VS provided in this case? Based on this equation, if you change this to 10,
$32.4.
okay.
I
Yeah,
agree.
if this number, Alan,
Yes, I got 32.4 as well.
2.4 kips. Is this good?
No. Are we supposed to reduce it or increase S?
Very good question.
Because we want VS to be small, right? So we're supposed to increase S.
So what is the current S in this design route?
The one you provide, the 10 one, or?
No, which one was the original one provided to us in the problem?
Oh, 14.
14. So he said that, Alan said that he'd like to reduce it from 14 to 10. How do you feel about this? Is this good or no? We should reduce it to a different number.
You should, I'm thinking you should increase it so that will give us VS value smaller, more smaller than when
Want to
we
reduce this? So you don't like 23?
Yeah,
So what is your target for this number here?
because at the end we want it to be less than 32.12, right?
Which one's gonna be less than 32? Why do you want it to be less? Do you want it to be
The
less or more?
summation, we're gonna add it together, right? VC plus VS with the feedback.
Okay, this is a very good comment. So I want to hear, let me review this again with
Excuse me.
Yes, Roman.
Can we just put, you know, right now we have the VS needed 25.76.
Yes.
And just could insert that in the V sub S equation. Instead of 23.14, we put 25.76, and instead of 14, just put S and then calculate. And I think we come up with number 12.5.
Okay, this is very good, but we'd like to take it here. We're just going through the steps this way. I agree with you, and this can be our common next step. But first, we're trying to understand why are we trying to reduce the spacing or increase the spacing and the effect of it. I agree with you, Ramin. This is correct.
Because we need to just increase the total number. So because the S is in the denominator, so we have to increase it.
Yes.
Yeah.
This is actually the discussion. Do we need to increase S or reduce S?
Reduce S because it's in the denominator. Because we need VAS in general to come up, to increase.
Excellent, Raman. So let's go back to Alan.
Yes.
Yes, Alan. Can you tell me why do you feel that you'd like to reduce S and not to add to it? Can you explain the whole thing again, please, in your words?
Yes, because you would be increasing the amount of reinforcement.
Why do you want to increase the amount of reinforcement? What is going on? Can you include it? Can you just discuss the whole thing, start from here? What's going on? Because I feel that some people needs to follow us the right way. So I need your help with this. What's going on here?
Yeah, okay, so originally you wanted to use the shear to, using the distance. So you had the 25.9, I believe.
Okay,
but
it means I was planning just use this 25. Okay, and then?
So I asked if we use the 32.12 instead because we weren't told to make it easier through the question.
Let's say, yeah. So this is just an assumption here. You'd like here to extend the problem and consider the shear demand to be 32.12, correct?
Yes.
Now I hope everybody here is following us. So continue, please. So what happened? Very good, Adam.
So using the 32.12, since the our V sub S no longer works for us, we have to change the spacing for the reinforcement, which would be the easiest thing to change in order to make the beam stronger.
So you'd like to reduce this because when this drops down, what's going to happen to this total number at the end?
It becomes bigger.
It's going to be going up. So you decided here to use 10 inches. So you have taken 10 inches, you put it in this equation. Am I correct?
Yes.
And then what happened? Your shear provided, or shear strength provided by the series is going to be 32. What number do you compare this to?
The 32.12.
Or you compare the 32 with this, or do you compare it with the 25.76?
Oh, sorry, yes, with the 25.76.
So, but this seems to be a lot now. It's much larger than this. So what other spacing that you'd like to try? Or do you feel that this is good enough?
No, after they commented on the V sub, plugging in the V sub S and solving for S to
Yeah.
optimize the equation. Yeah, I agree, and S should be 12.57.
How about if you try the spacing would be 12 inches? How much VS is going to be? Just quick thinking here. I'm using the same method. If I'm going to be doing here 12 inches, how much strength are we talking about?
27.
27. What number do you compare this to? If you say I'm going to compare it with the 25, right? The needed, VS needed. It seems good. So actually, I'm going to be going here with 12 inches. Can I put it as, let's say, 12.5 inches? Would that make sense to you?
Yeah.
You want to agree to it? Can you ask the people on the side to put it at 12.5 inch? Or they're going to be asking this, say, can you give us more practical numbers?
Well, if you do 12 and a half, the value is 25.92, which is pretty close to 25.76.
But can you ask the workers at the site to provide at 12.5 inch?
Oh.
Does this make sense? I mean, practical wise.
No.
Yes.
12.5, you're going to be going with them, you tell them 12 and 3/8 of an inch for the plate throughout the entire beam. That makes sense to you?
I understand. You want to use whole numbers for the inches.
So you'd like to have maybe 12 inches. So the numbers that I'd like to use is going to be 12 inches. I wouldn't use 11 inches, you know. Don't use 13 inches, right? So make it like 12 inch, maybe 10 inch if you want to, right? But don't use 10 and a half, don't use 11 and a half, don't even use 11. I'd use maybe 10 or 12, you know, some number like this. Like what you guys proposed, you said, well, why should I do this? Why don't I just find out the spacing? So different way of looking at this, you're gonna say now VS based on this equation equals, as you said on the top, 25.76. You say this is gonna be equal to 0.4, what is 0.4? AS, right? Times 60 times 13.5 divided by S. How much is the S that you're getting out of this equation? What did I do? I put the demand needed here. This is going to be the demand needed. It's not really ultimate demand, but this is going to be demand on VS to be 25.76. I put in this equation as if I added a number here, said, let me put here this VS to be equals to 25.76. And I said, how much would I get here for the spacing? What was the spacing out of this equation here? So everything is going to stay the same except for S.
The spacing would become 12.57.
Good. Now, what spacing should I provide? Should I go to 13 or should I go to 12?
12.
12. So I'm going to go a little bit smaller. Why? To be able that I have enough trends to cover this. Very good. Thanks, Alan, Oscar, Ramin, and Daniel. And also Alexander for today.
Excuse me.
Yes.
What if we just increase the AV?
How do you increase the AV?
The number of the ties.
Okay. It means that you want me to come here and then add one more tie in the middle, correct?
Yes.
So which one is easier? To keep the 14 inch or add one tie?
And now I'm just thinking that cost-wise, which one is going to be better? To adding another ties or just change the spacing?
I would change the spacing.
Because in a large scale, probably if you reduce, for example, 2 inches, maybe in 100 feet, the number of ties we use, set of ties we use, maybe is more than if you just add one another tie in between.
Are you going to be adding this one tie for 100 feet?
I just assuming that if
yes, no, I'm just asking. Are you going to be adding it at 100 feet?
Yeah, for example. It totally depends on what the scale we are working on, huh?
Exactly. And also, do you need this throughout the entire length of the beam? Do we need to add the tie at this spacing? This is going to be the other question here for you. For example, the shear here is high, right? at this location. But once you get away from this section, the shear demand is dropping down. So do I really need to provide all of this side throughout? You say no. Maybe at certain location, can we just provide the minimum? Don't you agree?
Yes.
So maybe in this section here, on this location, I'm gonna have lots of ties. And once I reach to a certain point, I'm gonna reducing the ties and put it at the maximum spacing possible. So it's gonna be like detailed design and more details that I'm gonna be getting into.
Thank you.
Now I'd like to check here the minimum reinforcement, right? For shear. I have these two equations. You guys have seen it. Where are these two equations? I'm gonna go back here to VS. There's two equations for the minimum reinforcement. I'm gonna be using it. Two simple equations. One of them, it gives you here AV minimum to be 0.11. The other one gives you here is gonna be 0.12. Be careful when you use any of F prime C or Fy here, it needs to be in PSI. The A sub V I'm providing is gonna be how much? 0.4 square inches. So I'm good, I'm covered, right? I said good. Let me look here at the diagram, try to understand it more. This is gonna be the end of the support, the column, shear diagram. And this is gonna be the reaction. You remember the reaction value? I guess by now we remember all of these values, right? 3212, the reaction. Critical section of shear. Where is the critical section of shear? It's gonna be this one. Gonna be our shear demand. How about this area here? What is supporting the shear in this location of the diagram? You see this part here is supported by the column. Right? Don't you guys agree? The column is supporting all of this. If I'm gonna go back here to this diagram, I said critical section of shear is gonna be happening right here. How about this piece here? It's gonna be part of the column and this hunch, which is like the column cap. So I don't have to worry about this because this here is supported by the column. And now this is gonna be supported by the beam. The concrete itself is supporting this. Look at this PVC. So what's supporting this shear from here to there? Yes, say what's supporting this shear here is gonna be the beam, the concrete, right? And what's supported by steel is gonna be this dark blue shaded diagram, if you like, with this petroleum color. So if I draw here a horizontal line for PVC, you're gonna see this section or this shaded section is gonna be resisted by concrete. If you like to go here to 1/2 of the concrete strength, once it hits or intersects with the shear diagram, this little area here, you don't really need any ties. Why? Because if the shear is lower than the shear demand, which means the diagram is lower than 1/2 of PVC, you don't really need any ties. In this section, from here to there, you can provide the minimum reinforcement needed. You have to. Why? Because you're going above 1/2 of PVC and you don't need any steel in this case. So you need to provide minimum. Well, the minimum is going to be matching with the minimum steel needed, which means PVC needed for the steel is going to be matching the shear demand, which let's say about a point here, this minimum reinforcement is going to be controlling in the general case. But the reality is we provided more than the minimum. If I'm going to go back here to this and look at it, look at this. What we have provided here is going to be more than the minimum. And it is making it right there. It is right there making it. So I guess this here is going to give you the location for the minimum shear. If you provide here the minimum shear, it's going to be supporting all of the shear diagram. Does it make sense? Any questions for this diagram? This diagram is more to understand what's happening, how the shear distribution works at the end of the beam. But when it comes to your exam, when it comes to any question or homework, you're going to be more concerned about the use of these equations. If you like to leave, go ahead. You can sign out. If you have a question, you can hang around.
If I could just make a quick little announcement for those of you guys who didn't see, if you guys want to join a little Discord for like a study group chat, let me know. Just send a message via my email or just direct message me here. But yeah.
So if anyone's interested, please make a copy of the chat. Would you like to put your name at the bottom or email address again, Alex?
Yeah, I'll do that right now.
Alex?
Just send me an email saying that you want to be invited. It's for iOS, Android, or even desktop.
Okay, great. Great. This is a good move, my friend.
Yeah, we're all going to be working together in the future, so might as well.
Yeah, absolutely.
Professor, are you going to be in your office hours in the other link?
Yeah.
Okay.